Let's wait for 2 3 minutes. And then I'll start. Okay. Let me switch off the video. So this is week 4. Problem solving session on mathematical methods in physics. One. So today, uh, the plan is to look for the Fourier series and Fourier transformation. These are the broad topics which have been covered in the week 4 contents. So we'll be talking about them. Okay. And we will do some, of course, after um, explaining these Fourier series and Fourier transforms, we can go for several questions. Okay. So in the beginning, uh, in the week 4 content, I have seen that there is a very little hint of simple harmonic motion. From simple harmonic motion, they show that the sine waves and the cosine waves, these are uh, easy to uh, represent and analyze. So, and then we will go for the Fourier series. So why do we do Fourier series and all these things will be covered. Okay. So initially, a very little about the simple harmonic motion. This is the first thing which is there. So if you define it, it is nothing but the motion in which the restoring force, the restoring force is directly proportional to the displacement of any mass or any body, okay, of the body suppose from its mean position or original position, you can say mean or original position. So this is the definition of the simple harmonic motion. So force, or you can say that the force per unit mass, that is the acceleration. So acceleration of a body, which we are talking about here, is suppose a, which is a function of time. Suppose it is changing with time, whatever it is, or remains constant. So that will be equal to or is proportional to the displacement from its mean position, and the proportionality comes out with minus omega square. So what happens is that why this negative? This negative represents the restoring part, the restoring force. So initially, if you have a body here and you try to displace in this direction, so there will be a restoring force in the opposite direction, A in this direction, which will which has the tendency to keep the body to its original position. This is the original position, right? So from the original position, we are trying to displace an object with some x, but there will be a restoring force which will be faced by that body that will be acting in the opposite direction, of course. And this is how it is. Uh, it is written, and this kind of motion is nothing but the simple harmonic motion. And in the simple harmonic motion, you have oscillation, like simple harmonic oscillation. Simple harmonic oscillation will be there based on the same principle. It works. Okay, simple harmonic oscillation, which is represented as some displacement y displacement, which is equal to some amplitude, and we generally represent it with the sinusoidal features like sinusoidal functions. Okay, it can be sine, it can be cosine, anything. Okay, sine omega t plus phi. This is how we define the oscillation. So now here we represent A as the amplitude of the oscillation, amplitude of oscillation. Next is your omega, which is nothing but the frequency of oscillation. Actually, it is not the frequency, but it is the angular frequency. Okay, so fine. This is the frequency of oscillation. You can see. Actually, it should be omega by 2 pi. That should be the frequency of oscillation. Okay, represented by S. Okay. Next is the time period of oscillation. So time period is what? This is 1 by S. So this is called the time period of oscillation. Okay. So this is another thing, and if you write it, it should be 2 pi by omega, just the reciprocal of the frequency which I mentioned. And the initial phase is represented as the pi. So this is the initial phase, starting phase. So this is the initial phase. And in total, whatever the argument of time is there, this omega t plus pi, this is nothing but the phase angle or phase. Okay. This is the phase of the oscillator. Okay. So we will be dealing with the mathematical part of this and not much with the physics here. This can be detailed in detail can be covered in the waves and oscillations part of the physics. Okay, so you can go through any books or NPTEL lectures. Fine. So one of the examples, if I have to give for this particular oscillatory system, is suppose y is equal to 3 sine, you have 2t plus pi by 4. If this kind of a oscillation is being represented, then we can say that the phase is nothing but 2t plus pi by 4. Of course, it depends on the time. And the initial phase is pi by 4. And see, this is 2 times t. T is the time, and this will be the omega, the angular frequency, which is equal to 2, and its unit is radians per second. Okay, and because it is angular, that's why its unit is radians per second. Otherwise, if you write the frequency of oscillation, that will be I have shown that is equal to omega by 2 pi, right? So it will be 2 upon 2 pi, which is equal to 1 by pi. And now it will not be a radians per second, but it will be per second, which is nothing but hertz. Hertz is the unit of the frequency, right? So this is another thing. Okay. Now, what is the time period? We know that time period is nothing but the inverse of the frequency, which is nothing but pi seconds. Time periods unit is seconds, of course. So this is the thing. And the most important thing is that the amplitude of the oscillation is 3. Okay. So this is what how the oscillations are being represented. So yes. Okay. So what is happening is now, okay, fine. Let us take another example and then we can illustrate everything. So this is another example. Now, instead of giving some mathematical values into the oscillation characteristics, which is defined by this, now let us take a generalized case. Say y is equal to a sine say omega t plus phi 1 and plus a sine omega t minus phi 1. So you can see that the initial phase there is a change. Like in one case it is minus pi 1, another case it is plus pi 1. Okay. So now if you do this, easy, just simple trigonometric formula. So sine omega t plus pi 1 plus sine omega t minus phi 1. Okay. So A will be here and we can solve this. This will be, I think, 2 times sine of just this A plus B by 2. So it will be omega t plus phi 1 plus omega t minus phi 1 divided by 2. And again, it will be cos omega t plus phi 1 minus omega t plus phi 1 because there is a minus divided by 2. That's all. Right. So 2 can be taken outside, 2a. What about here? Omega t cancels out. This will be 2 phi 1 by 2. And here phi 1 cancels out and 2 omega t by 2. So what you will get? Sine omega t. And here it is cos phi 1. Right. So you can see clearly that this cos phi 1 is nothing but some constant value. It's not a function of time. Constant with respect to time. Okay, so you can take it out. So 2a cos phi 1 will be there and there will be sine omega t. Now, the new amplitude, after solving all this, the new amplitude becomes this. So this is now my amplitude. Okay, and what about the, so omega will be definitely the angular frequency or you can derive frequency from here. And that's all. And there is no initial phase. You can clearly see there is no initial phase. So whenever you have two sinusoidal functions adding, first you have to first solve it using trigonometric identities, and final result has to be interpreted. So this is the final result which we are getting, and we will get this no initial phase angles. Okay, no initial phase angles. All right. So this is one of the part. Fine. Next is that, okay, if you just suppose you have, let us take another example, not very difficult. This is A sine omega t plus phi, very general oscillation characteristics represented in the mathematical form. Now, if you do a time derivative of this, what will happen? So this is the displacement of the particle, right? This is the displacement of the particle, which is represented as an oscillatory form with time and phase and with frequency. Now, if you do a time derivative of this, what will happen? It will give you the velocity of the particle's oscillation. Okay, so what it will be? Just differentiate sine omega t plus phi. We are differentiating with respect to time. So it will be A omega sine will becomes cos omega t plus phi. Right? So this is what you will get. Fine. So it will be some way, some omega times some A cos omega t plus phi. So you can see in other way around. So v, the velocity, is some omega times some kind of a displacement. This cos omega t plus phi or sin omega t plus phi has only a difference of a pi by 2. Only the phase angle will change. Other things will remain the same. Okay. So it is somewhere related to omega times some kind of a displacement feature. Okay. This is one of the important things. Next is the concept of waves. So just a little bit of the feature I wanted to give. So what is the difference between this oscillation and waves? It's simple like this. So suppose you have, this is suppose y axis and this is x. Okay. At any instant of time, system t is equal to t naught, instant times, you will see that this is a medium, suppose, and it has particles here, and we have given some perturbations to this particular thing. So you'll see that this particle goes here, this particle goes here, is here, like this. Okay. So in this way, it is the particles are oscillating. Okay. So you can see that you can just put an envelope of this, and this becomes the wave, which now for the time being it is instantaneous, but with time you will see that this wave is propagating in this x, positive x direction or negative x direction, any direction. So with time, a wave will propagate. So what will happen in this wave is that when the wave is propagating, see these particles, whatever the particles are here, these particles will remain fixed. I mean, these particles will not move in the x direction. Okay, these particles will not move in the x direction with time or in time, whatever you say. Okay, so as the time increases or the time changes, these particles will still be present here. So if this is the P1 particle, this P1 particle will be there. Particle will be there, but with different oscillation characteristic. Okay, so what I'm trying to say is that suppose there is P naught, which I have shown. So at some T naught plus delta T, so T is equal to T naught plus delta T, increasing time, this is X, this is Y. This particle P1 may have no oscillation or small oscillation. This will be here, this will be here, this will be much more. This is somewhere here, somewhere here, like this way. So it will go like this. Okay, so this P1 will still be here, but you can see that its oscillation or the displacement by this P1 is somewhat lesser than this. But P1 remains there. That is the most important thing. Okay, P1 remains there. And you can see that this oscillation will continue. Okay, so let me just quit. clear it and make it again so that it will be clear. This is your x. So what is happening is that here, suppose you have no displacement, you have some small displacement. Here, this will be like this. This has now gone up, down. Okay, so you can see that this is how things will be propagating. So you can see that the peak, which is here now, it has now come somewhat in this direction, or it is propagating in this direction. Just for showing, I am just giving. Okay, so P1 particle will remain in the same place. Okay, will be there in same place, but with different y displacement with time. Right, with time. This is what it is. So it will. So wave will transform momentum and energy in plus minus x, whichever direction you wanted to transfer. So it will transport energy in plus minus x direction, but medium remains undisturbed. Medium will not change, so it will remain undisturbed. So the particle, wherever it is, it will be remaining there. Okay, so this is the general of waves, and wave equation is like this. Not the wave equation, this is the solution of the wave equation. It can be represented either by sine or cosine or exponential iota. So it will be, you can write kx minus omega t or omega t minus k, or a cos kx minus omega t. So whichever way you want to generate, this is how you can generate. And in general, the phase velocity is given by some omega by k. This is the Cp, phase velocity. Okay, means suppose you have this instant phase, some phi. This phase is moving in what, or what is the value of the velocity here? So this is the Cp. Okay, so this is what the basic general introduction of the harmonic oscillations and the waves. Okay, what interesting thing is that both for the simple harmonic oscillation, so we see that both for oscillations and waves, we use sinusoidal functions because these are easy to interpret. Okay, sinusoidal functions. Okay, so sinusoidal functions which are easy to interpret. So that's why we generally use the sines and cosines to represent the oscillations or the wave characteristics in the mathematics. But so we will try to see that how we can convert any arbitrary functions, but with some conditions, of course, with certain conditions, how we can represent those functions in terms of sines and cosines. Because every time you will not get the exact sine and cosine functions, you may get some, say, functions like x, some other functions, whatever it is. Okay, some tan x or whatever it is. But we can convert it or we can write it in terms of sines and cosines. That is the most important part. Okay, fine. So let's now start the concept of the Fourier series. But before going to Fourier series, let's dive into the concept of periodic function. So what is a periodic function? You will see that this periodic function is an important criteria for the Fourier series. So to write any functions in terms of sines and cosines. Fine. Let's first define what is a periodic function. So some preliminary aspects we must know. Then we should dive into the Fourier series. Okay. So now, how to define it? So suppose if a function If a function fx repeats itself after equal intervals of x, then fx, the function, is called the periodic function of x. Okay, so and the interval which we are talking about, this interval is the period of the function. If this x is time, then it will be the time period. If it is some space, it will be some spatial period. Okay, so this is periodic or the period of the function, period of fx. Okay, so how to represent it mathematically? So this is some function. We are actually saying that x plus some t will be equal to f of x, where t is the period of the function. All right. So this is what the periodic function looks like. So if you have to further elaborate this thing, you can write this that f of x is nothing but f of x plus t is equal to f of x plus 2t, so on, is equal to f of x plus n times. That's all. This is what the periodic function looks like. So every time period t, like x plus t or x plus 2t, so you can see that after a gap of t, the function remains the same as x is equal to the starting point. Okay, so let's talk about the period of the function, how to calculate the periods. Okay, so for calculation of period, suppose we have the sine nx or cos nx, whatever. Okay, so we define time period of them as 2 pi by m. We have seen this already. We have looked at the simple harmonic oscillation where we were writing sine omega t plus pi. We are writing this omega or the frequency of oscillation as omega by 2 pi. Just the opposite is the time period, and that is what I have written. Instead of omega, it is n. Okay, so this is your time period. This is the period. All right. Now, so if you are being given sine of x, then what will be its period? So its time period will be, or period will be 2 pi by 1, because m is 1 here, so this is 1. So it will be 2 pi seconds or whatever the unit it is. Okay, so what does it represent is that you have a kind of an oscillation like this. This is a sine wave, simple sine wave. We know that at pi it is 0, at 2 pi it is also 0, and at 0 it is 0. This is pi by 2, and this is 3 pi by 2. All right. So we know this. This is suppose x. Now the thing is that you can see that this entire cycle, this one complete cycle which it has covered with one maxima and one minima, this has the period of 2 pi. Now next, it will go like the same way. So with a period of 2 pi. Okay, so this is 2 pi, this will be 4 pi. Okay, so this is the periodicity. This is the periodic function. Okay, now fine. This is one of the examples of sine and cosine. Let's take another example. Let's take some amplitude A sine x plus B cos x. Now, in all these things, you can see that just check what is the time period of the first function. Just look at the sine x, the sine part. Okay, and you have one here, so its time period will be 2 pi. What about here? Cos, again, sine and cos are only the same thing. There is no problem, but only the phase difference is there, pi by 2. But we are talking about the omega. So here it is also 1. So the time period will be also 1. Right? So what will happen is that the resultant The resultant will be a sinusoidal function, definitely a sinusoidal function with time period or period is equal to 2 pi. We generally take the LCM of the two periods whenever these functions are being added. Fine. Another example, A sin x plus B cos 2x. Now, what is the time period here? This is 2 pi, of course. What about here? 2 pi by 2. This is time period here. So, this will be pi. Take the LCM of these two. So, LCM of pi and 2 pi. And what it will be? It will be 2 pi. Fine. Here, what happens is that the resultant will be a non-sinusoidal periodic function with period which is equal to the LCM of the two, which is equal to 2. Okay, this is another example. Let's take a non-sinusoidal function now. Okay, say a non-sinusoidal function. Okay, this is a non-sinusoidal function, and let's take this is a tan mx, and this is a periodic function. Suppose. Okay, this is a periodic function. So tan mx, its period again will be t is equal to 2 pi by n. Okay, and how will you represent this? Is something like this, where suppose n is equal to 1, we are talking about. Okay, so this is pi by minus pi by 2, pi by 2, and 3 pi by 2. So we will see that the graph looks like something like this. Okay, and okay, so pi by 2 and okay, this is pi by 2, this is 3 pi by 2, this is 0, this is minus pi. So you can see that there is some kind of a repetition of the functions. Okay, so this is another way of representing. I think this will be some pi by n. Okay, so yeah, this is what it is. Fine, these are some particular examples of the periodic function. Now, let's come to the Fourier series. Okay, so once we have talked about the periodic function, let's come to the Fourier series. All right. So, before going to the Fourier series, we will talk about its applications, and then we will go to the formulation of the Fourier series. So let's talk about its application. Why do we need to do this Fourier series? So what happens is that suppose you have a non-sinusoidal function, so any non-sinusoidal function, it will be x, the simplest constant function in a particular period. So it has to be, look at the line. So a non-sinusoidal periodic function can be represented in terms of sine and cosine functions, which are easy to analyze. Right? This is very the properties of sine and cosine are very well known to us. So that's why we generally try to fit a sine relationship or a cosine relationship. So that's why it is easy for us if we can represent any non-sinusoidal periodic function to sines and cosines, sine and cosine function, or we will see that there will be a complex exponential function. Okay, because these are easy to represent. and analyze. Okay, sines and cosines, sines or cosines, easy to analyze. That's the reason why we require Fourier series to convert any non-sinusoidal periodic function. It has to be important. This is periodic function to be represented in terms of sines and cosines. Why sines and cosines? Why not any other functions? We will see why we do that. Okay, we'll see that. But before that, the important thing is that there are several conditions. The conditions for representing a function in terms of sines and cosines. Or you can say that the conditions for the Fourier series. So conditions for Fourier series representation will be what? Okay. So conditions for Fourier series. This we popularly is popularly known as the Dirichlet's conditions, which are extremely important to be followed, and then only a Fourier series can be represented. So the Dirichlet condition. So how? What are those Dirichlet conditions? So I will list it down and try to explain. Number one is that if suppose a function f of x is defined in a b, some closed interval a b, okay. So this is the general statement. One is that this fx, which is being defined in a b, in a closed interval a b, this fx should be a single valued. This should be a single valued and bounded at all points in a given interval. All right. So this is one of the things. So what do you mean by a single valued function? A single valued function, as the name says. So suppose you have a function something like this. You have one value of x and its corresponding value of fx. You cannot have one value of x and two values of fx, just like the case of a parable, where for one x you have two values of fx. This is also some fx. Okay, so this is not a single value, okay, but this is a single value function. Important. So this is one of the point that it should be single valued and bounded between certain intervals. Okay, number two is that, which is very important, that fx should be periodic outside a b. See, this is now the open interval a b. So outside the open interval AB, fx should be periodic. For example, just like the sinusoidal wave or any wave. Okay, so you have 0 to 2 pi. Now I'm saying that outside this 0 to 2 pi, it should be periodic. That means it should continue to be like this. Okay, this is what I'm talking about. The dark shaded line. Okay, outside 0 to 2 pi, this should be periodic. Okay? This is what is being said here. Third is fx should have finite number of maxima minima. Okay, where in the closed interval a comma b. In a closed interval, in a closed interval set, there must be finite number of maxima minima. Number four, is that fx should have finite number of discontinuities. So the important and powerful thing of this Fourier series is that it also can represent a discontinuous function, but it has to be satisfying all other conditions like periodicity and whatever. Even it can represent a discontinuous function into sines and cosines. Okay, discontinuities. But it has to be finite number of discontinuities. For example, a square wave function. Okay, so this is, say, suppose minus pi. This is suppose pi, and you have a function like this. Okay, so where is the discontinuity coming? So minus in between a comma b. Remember in this. So in between minus pi to pi, you have one discontinuity here, another discontinuity here. This we will not include because we are considering just before the pi. So this is one discontinuity, this is the other. So there are two discontinuities, which is finite. So we can represent a square wave or a rectangular wave uh, in terms of sines and cosines. Fine. So these are the four important Dirichlet conditions. Most important is the periodicity. Okay. So if these conditions are followed, so if these conditions are followed, then we can write fx as some a naught, or you can say some a naught by 2. Sometimes people write. Okay. This is k is equal to 1 to infinity ak cos kx plus sin k is equal to n 1 to infinity bk sin kx. This is how you can write. Okay. Now you can further generalize this as fx as a naught by 2 plus k. You can leave it as it is. Now this can be written as a k cos 2 pi ax divided by b minus a in some arbitrary interval a comma b, and this is for, say, suppose 0 to 2 pi or minus pi to pi, whatever. Okay, for this it is this, and for general interval k is equal to 1 to infinity bk sin 2 pi ax divided by b minus. Okay, this is how we can write. Where this part a naught by 2, see, you can write a naught also. Okay, this can be written as, this can be a naught also, but there is a reason why we generally write a naught by 2. I will show that while we can compute the the a naught, how to compute the a naught, ak and bk's. Then we will understand that why we write it a naught by 2 intentionally. Okay, so this is for ourselves only, we do it a naught by 2. So what is this? This is actually the mean component. Okay, mean component of any time series. Okay, mean component. So any signal, its mean is given by this part, or in electronics it is called the DC component. Right, and these are the fluctuations. This ak cos k sine, these are the fluctuations. You can see that the sine oscillations, fluctuations. Okay, so one part, these cosines and sines represent the fluctuations, or in electronics it is called the AC fluctuations, alternating current, whereas A naught by 2 is the DC, mean value. Fine. So this is the important part. Now question is that why sines and cosine? Why we write any functions, non-periodic functions in terms of sines and cosine? Why? So here what happens is that we represent orthogonality. We tend to try to develop the concept of orthogonality, just like we know that I cap, j cap, k cap, these are the orthogonal, mutually orthogonal unit vectors, right? The orthogonal unit vectors. And we know that I dot j is equal to 0. This is the orthogonality. And I dot I is equal to 1. And hence we can write any vector v as some vx I cap plus vy j cap plus vz. Okay. So this same orthogonality, same concept of orthogonality concept, we apply to the sines and cosine. And let's see what happens. Okay, let's do it. Let us see what happens when we integrate 0 to 2 pi sine kx and cos mx. Why sine and cos are ready? This is because you can see that here it is one part it is cos, one part it is sine. Okay, so that's why I take in general some sine kx and cos mx and integrate it between 0 to 2 pi. And this actually represents the sine mx, oh sorry, kx and cos mx inner product. So this is the inner product integration. We need inner product. In terms of integral, we write it like this. Okay. So let's check one first criteria that when k is equal to m, then what will happen? So it will be 0 to 2 pi sin x or sin kx cos kx. Because k is equal to m. Now we divide it by 2 and multiply by 2. So you get 2 sin kx cos kx. And very known expression in within the integral, that is 0 to 2 pi, this becomes sine 2k, correct? And we know that 0 to 2 pi integration of sine anything is 0. You can try it. This becomes what? Half. This becomes cos 2kx with a minus sign divided by 2k, and it goes from 0 to 2 pi. Cos 2 pi is 0, cos 0 is uh, yeah, okay. So this is, if you just put cos 2 pi, this will be 0. And if you put 0, it will be some minus 1, right? So in this way, uh, we can, yeah, I think it is fine. Okay. So we just put k is equal to 1 for the time being. So we get half just for a representation. Let's say k is equal to 1. So we get minus cos of 2x divided by 4. So you get 0 to 2 pi, and you get this as 1 minus 1. This is equal to 0. Okay, so this is 0. Now, if k is not equal to n, then also half, again, if you just do the integral, 2 sine kx cos mx dx. So what will you do is that 0 to 2 pi sine of k plus m x. This is also known. Okay, uh, just writing this expression in terms of trigonometric identities. Okay, dx. So sine of anything from 0 to 2 pi will be always 0. So it will be half times 0, which is equal to 0. Okay, right. Fine. So yeah, so even if you don't do it, it will still come. See, you don't need to do k is equal to 1. So half this, if you put 2 pi, you know that cos of 0 is 1, cos of 2 pi is also the same, right? Because it's a 360 degree, the 2 pi is nothing but the 360 degree. This is nothing but again coming back to the 0. So it's an oscillation which is coming back to 0. Okay, so this is 0, this is also 360. And all of them, it is always cos will be equal to 1. So whatever it will always be 1 minus 1, which is equal to 0. Okay, so both the cases, you can see that integral 0 to 2 pi sine of kx cos of mx is always equal to 0 irrespective of k is equal to m or k is not equal to m. In both the cases, it will always be 0. But now if you do 0 to 2 pi is sine kx into sine mx dx. If you do this, you will find out that this comes out to be, you can do it on your own. This is pi and this is 0. When k is equal to m, this becomes pi. When k is not equal to m, it is 0. Similarly, if you do 0 to 2 pi cos, this is, I would like to check, this will happen. Okay, cos kx cos mx dx. So this will give you again pi, it is 0, k is equal to m, k is not equal to m. So what we can see here is that when you are taking the inner product or integral from 0 to 2 pi, sine into sine, you are getting some value at certain point. Cos into cos, when you are doing inner product, you are getting some value at a certain point. But if you when you are doing sine and cos, it will always be 0. Just like we did that, it is just like I dot j. This is just like I dot I, and this is just like j dot b, j dot j. This is always equal to some value 1, but this is always orthogonal. So sine and cos forms orthogonal basis. That's why, okay. So the concept of basis comes here. So sine and cos are mutually orthogonal. So these are mutually orthogonal, and that's why we can write any non-sinusoidal periodic function in terms of sines and cosines. Okay, this is the reason why we write any function in a periodic form or certain conditions being followed in terms of sines and cosine. Why? Because they are mutually orthogonal. It forms some kind of a basis. Fine. So this is another thing. Now let's do some play with what we have got. Okay. Fine. So let's. So what we have got finally. So you have f of x is equal to a naught by 2. You can write a naught also. It's fine. Same thing. K is equal to 1 to infinity. Ak cos kx plus k is equal to 1 to infinity b sin kx. Correct. This is what the expression is for 0 to 2 pi. Now what happens is that you can write this. If you don't want to write a naught by 2 here, you just can keep it a naught, because a naught by 2 a naught same. Okay, so you can keep this so that you can generalize this as the k is equal to 0 to infinity ak cos kx. You can clearly see that if k is equal to 0, this will be 1. Okay, so k is equal to 0, cos kx will be equal to 1, and ak will be equal to a naught. So a naught will be included here. Similarly, k is equal to 0 to infinity, some bk sin k. Now what happens is that at k is equal to 0, sine of 0 is 0. So b0 can be anything. Okay. Anything you can do, but this will be always 0, right? So it doesn't matter. Fine. So this is one of the another important thing. So now let us do a question so that we can. Okay. So let us say f of x is equal to say cos square x. Now what we can write? So question is that uh, what are the values of a naught, a1, b1, okay, and a2. Fine. So fx is given as cos square x, right? What we can write about the cos square x? We can write this as this cos 2x by 2. So what is this? This will be half. This will be half cos 2. So a naught will be equal to some half. A1 will be equal to half. Sorry, 0, because there is no a1 term with cos 1x. And a2 will be equal to half again. And b1 will be what? Nothing is there. No sign terms. So it is not there. Alright. So this is one of the parts. Okay. Fine. Now let's find out what will be the values of uh, expressions expressions for a0, ek, and 2. Okay, this is what the next thing which we will find. Okay, so fine. Let's take the example for fx. We'll take that b minus a is equal to 2 pi, or it is 0 to 2 pi. The interval is 0 to 2 pi. So fx can be written as a naught. I'm not writing a naught by 2 here. K is equal to 1 to infinity. Ak cos kx. We know that from 0 to 2 pi it will become like this. And k is equal to 1 to infinity. Dk sin kx. Fine. Now, just look into this particular expression. Suppose to find a naught, what to do? See, if we just directly put dx and integrate it from 0 to 2 pi, it will be cos dx from 0 to 2 pi. It will be sin kx from 0 to 2 pi. Right? So we know that from 0 to 2 pi, both cos and sin will be always 0 if you integrate from 0 to 2 pi. So this will be 0. Only thing will remain is this. So let's do that. To find a naught, let us integrate both sides with x from 0 to 2 pi. Okay. So if you do this, your left side becomes fx dx 0 to 2 pi. Right hand side becomes dx from 0 to 2 pi. Summation, leave it as it is, it does not matter, is equal to 1 to infinity. Integrate 0 to 2 pi a k cos kx dx plus summation again k is equal to 1 to infinity 0 to 2 pi bk sin kx dx. And we know that these will be always 0. Cos and sine integrals from 0 to 2 pi is always 0. So what you get finally is 0 to 2 pi fx dx is equal to a naught times 2. So a naught will be equal to 1 by 2 pi integration from 0 to 2 pi fx dx. This is the first part. Now here you will see that why we sometimes write a naught by 2, why we sometimes write a naught. It all depends on the definition. Remember. Okay. Next, the second part is that to find ak. Okay. To find AK, let's see what is the expression. This is the expression, right? This is the first expression. We need AK. So what to do? The best thing is that if we can multiply with cos kx in both sides, we know that sine into cos integral from 0 to 2 pi we have seen that is equal to 0. And here it will be if you write cos kx and integrate it from 0 to 2 pi, this will be also 0. Remaining will be this. Okay. So what we will do is that to find AK, let us integrate with cos kx dx. Okay. And from 0 to 2. So let's do it. So in the left hand side, we have 0 to 2 pi fx. So with what we are integrating? Cos k. On the right hand side, we have 0 to 2 pi. If we write it, a naught cos kx dx plus summation, leave it as it is, 0 to 2 pi ak cos square kx dx plus summation 0 to 2 pi bk sin kx cos kx dx. All right. With this, you can see that this will be 0. This will be also 0. We have proved it. This also is known. So what you will get finally is that just leave the summation for the time being. It will be AK and cos square kx is what? 1 plus cos 2kx by 2. So it will be half dx. So it will be half into 2 pi. So it will be pi. And on the other side, it will be 0 to 2 pi fx cos kx dx. So AK will be equal to 1 by pi 0 to 2 pi fx cos kx dx. This is the equation. Alright, this is the expression. Similarly, I am not doing it for bk. We integrate with sin kx from 0 to 2 pi. So finally, the expression of bk will be same 1 by pi 0 to 2 pi fx sin kx dx. This is the expression. So the one thing to note is that for AK and BK, just before the integral you have 1 by pi. But in case of A naught, you'll see this is 1 by 2 pi. That's why we define A naught by 2, and hence we can write this as 1 by pi 0 to 2 pi fx dx. Okay, this is how we write. And that's why we in the beginning write that A naught by 2. Okay, so this is important. So you have to remember that if you are using, suppose this is the question, in general, if you do, you have to write a naught as half. But if you are not willing to do this and try to do with a naught by 2, then you have to compute it with 1 by pi, 0 to 2 pi, and then cos square x. Okay, so remember this a naught at that time will become a naught by 2. So that is very important. Right? So this is important, right? Okay. So this is so you will find that here your a naught by 2 is actually, so this is your a naught by 2, right? So this will be, you have to integrate with this. So it will be, I think, 1 plus cos 2x by 2 if you have to integrate it. And yeah, so it will be, I think, some 2 pi by 2, and there is a pi. Okay, so this will be something like 1, so something like this. Okay, so this is how it will be. Fine. So okay, Fine. So this is how the expressions looks like. And if you have to generalize in between limits a and b, you can write your a naught as 2 upon b minus a to b fx dx. Your bk will be equal to 1 upon b minus a to b fx sin kx, not sin kx, but it will be 2 pi kx upon b minus a because it's a generalized expression. And your ak will be equal to 1 upon b minus a to b fx cos 2 pi kx upon b minus a dx. All right, so these are the few things which needs to be done. Okay, fine. So once we do that, now we can go ahead with the complex Fourier series, which is the next topic. So let's do that. This complex Fourier series will lead to the Fourier transform also. And we'll stop after Fourier transform because that is the last part. And then we can solve some questions in the remaining time. All right. So, yeah. So the next thing is the complex Fourier series. Before that, just let me write the expressions again, which is a naught summation k is equal to 1 to infinity. Right. So this is what it is. Next is ak cos kx plus summation k is equal to 1 to infinity bk sin kx. So we are again writing in terms of 0 to 2 pi. Okay. Now we know that cos kx, cos can be written in terms of exponential iota like this. Correct? This plus minus iota kx divided by 2 and sin kx e to the power iota kx minus e to the power minus iota kx divided by 2i. This is important. Okay, now if we just put it in this particular series, we get the complex part. So fx will be equal to a naught plus summation k is equal to 1 to infinity ak. So e to the power iota kx plus e to the power minus iota kx divided by 2 plus summation k is equal to 1 to infinity again dk. This will be e to the power iota kx minus e to the power minus iota kx divided by 2. This is the expression which we are getting. Now, what simple thing, e to the power iota kx terms we will separate, and e to the power minus iota kx terms we will separate. So simply k is equal to 1 to infinity ak minus iota this iota can be written like this, right? So minus iota, right? So we can write like this. So minus iota bk divided by 2 e to the power iota k plus k is equal to 1 to infinity again. This will be ak plus iota bk by 2 e to the power minus iota kk. Some changes which will be somewhat different. So what will happen is that I will change this k to minus k. Okay, once we do that, what happens is that you keep the first two terms same, k is equal to 1 to infinity. This becomes ak minus iota bk by 2 e to the power ikx. This is fine. Plus, now this k will be from minus 1 to minus infinity because k now has become minus k. A minus k plus iota b minus k divided by 2. This will be e to the power iota k because k becomes minus. All right, this we can do. Now, let's look at what will be the expression of a minus k. So, we know the definition. This is 0 to 2 pi ak, or sorry, this is fx cos of, now there is a minus k, right? So minus kx. Cos of minus kx will be what? This is nothing but 0 to 2 pi fx cos kx. Cos of minus kx is cos kx. So this becomes equal to ak. There is no difference. What about b minus k? 1 by pi 0 to 2 pi fx sine of minus kx dx. What it will be? 1 by pi 0 to 2 pi. I know that sine of minus kx minus sine kx. So what we can write this as minus b of k. So now, if you have to write it again, f of x will be a naught plus summation k is equal to 1 to infinity k, sorry, minus iota bk by 2 e to the power ikx plus k going from say minus infinity to minus 1. A of minus k is ak, b of minus k is minus bk. So this will come. Both are e to the power iota kx, so we generalize it. A naught, combining the sign from minus infinity to infinity, but k not equal to 0. See, we don't have 0 here. So it will be ak minus ibk by 2 e to the power I k. Almost final expression we have got in terms of complex Fourier series. Okay. Now we can tell this as some c of k. So this is only just a notation. You can write it. It's up to you. The k tends to not k but equal to. So this k should not be equal to 0. Ck e to the power iota kx. Now in the same way, if you have to find out what is the ck, then what you will do? Ck will be nothing but still it will be just 1 by 2 pi 0 to 2 pi. Okay. Uh, fx e to the power minus ik dx. See, if you do it in both the sides, so it will be 0 to 2 pi fx e to the power minus ikx dx is equal to say 0 to 2 pi a naught minus ikx dx plus summation does not matter tk. This will be 1 dx 0 to 2 pi, and that's why this is okay. Now let's take c of 0 for k is equal to 0. What it will be? 1 by 2 pi 0 to 2 pi fx dx. What was that? A naught. So a naught can be written as c naught. So fx can be written as therefore c naught plus whatever was there. Let me write. minus infinity to infinity, k is not equal to 0, pk e to the power ikx. Or we can combine this as k is equal to now minus infinity to infinity, ck e to the power ik. This is the final expression of the complex Fourier series. So this is your complex Fourier series, where your ck will be equal to 1 by 2 pi, then same definition, 0 to 2 pi, your f of x e to the power minus. That's all. All right. So this is the complex Fourier series. And so before jumping into the Fourier transform, let's just write it. The Parseval's theorem. Okay. And let us discuss about the even and odd functions also, and do some questions about the Fourier series. Once that is over, we'll go for Fourier transform. It will not take much time. Okay. So let's go for the questions. But before going to the questions, I think let me just quickly talk about the even and odd functions. Okay. So even and odd functions. All right. So f of minus x. So f of minus x, if it is equal to f of x, then it is even function. Right? This is the very general definition. But f of minus x, if it is equal to f minus f of x, this is odd function. All right. So one example of odd function is sine. Sin x is the example of odd function. Why? Because if you put sine of minus x, it gives you minus sin x. And one example of even trigonometric function is cos x, because cos of minus x is equal to cos x. Then another important feature of the even and odd function is this. For an even function like sine, sorry, the odd function like sine, you have something like this. This is the sine function, right? And for cos x, which is an even function, so this is even and this is some odd. So cos will be like this, correct? So you can see that it is symmetric about y-axis, but this is symmetric about origin. This is the difference between the odd and even. So when you have to integrate this, say from minus pi to pi, so if you integrate this from minus pi to pi, you cannot change much. Okay, but if you have to do this, say minus pi to pi cos x dx, you can write this as 2 times 0 to pi cos x dx. Right? So this is 0 and pi is here. Right? This is minus. So this is how you can uh, do the integration. Okay, right. This is all about the even and odd functions. Let's go for Parseval's theorem. I just will write the thing, okay, and not explain much. It's not time is not much left. So Parseval's theorem is that simple means if you have your 1 by 2 pi integration from minus pi to pi. not from now 0 to 2 pi, I'm writing minus pi to pi. So you have f of x square dx. This becomes, see, this is square, right? So it will be nothing but half a naught square plus half summation q is equal to 1 to infinity ak square plus bk square. Or in terms of complex, it becomes minus pi to pi fx square dx is summation a going from minus infinity to infinity mod ck square. Okay, so these are the two important things to note about Parseval's theorem. This is how we can write it. Okay, and you can see that we will be using this to get certain expressions, right? So let's do that. Some questions let us do, and then we will get back to the Fourier transform. Okay, the first question is that using sine series with fx is equal to 1 from 0 to pi, prove that pi square by 8 is nothing but 1 plus 1 by 3 square plus 1 by 5 square plus so on. Okay, remember, question says that only of the sine series. All right, so let's do it. Sine series means what? Only the bk sine k part, correct? This is what is required. Okay, let's find out bk first. What is the definition? 1 by pi, 0 to 2 pi, fx sine kx dx. Correct? So bk 1 by pi, we only have from 0 to pi, right? We don't have any other things. So this will be 1 sine kx dx. So what it will be therefore 1 by pi sine kx dx from 0 to pi. Remember, this is not from 0 to 2 pi. Okay, so this will not be 0 here. So it will be 1. So it will be 1 by pi, which will be there, of course, and yeah, it will be now. So wait, yeah, so it will be 1 by pi definitely, and this will be minus cos kx divided by k from 0 to pi. All right, so this will be 1 by pi, and with the minus sign, minus I am taking outside, k also I am taking outside. This is k. Okay, so k I am also taking outside. So cos of k pi is minus 1 to the power k and minus 1. This is what you will have, right? Now, if your k is odd, if your k is odd, then what will happen is that your bk will be equal to minus 1 by pi k. So it will be minus 2, means it multiplied by minus 2. So it will be about 2 by pi k. Fine. Now, if k is even, then what will happen? This will be simply 0 because minus 1 to the power even is positive. So therefore, bk will be equal to 0. So we can write this f of x as some 2 by pi sin x plus 2 by 3 pi sin 3x and so on. You can write another term. So 2 by 5 pi sin 5x and so on. You can go ahead. All right. So now 0 to pi. Now if you do fx of square dx, this will be on the other side. You have that your this 2 by pi will be there, so it will be 2 by pi square plus 2 by 3 pi square, right? Plus 2 by 5 pi square, and so on, right? So this is another thing which we will get. And your 0 to pi sine square x, that also we have to see, right? So, right. So this is, I think, mostly done. So this is 1 in this part. So this will be nothing but pi. And here also something will come, right? If you look at the Parseval's theorem, you have here 1 by 2 pi, correct? So I think here also you will get something like this, or it will be some 2 pi kind of thing will come. Okay, so here it will be 2 pi. So this will give you, so this pi and pi will go, and this will remain. Okay, and so on. So finally, what you will get is that, so you have your, so this will be 1 by 2, and on the other hand, you have your 4, and pi you can take, pi square you can take outside. So you get here 1 plus 1 by 3 square plus 1 by 5 square, and so on. We've already reached the destination. So it's just pi squared by 4 to the 8. That will be equal to 1 plus 1 by 3 square plus 1 by 5 square, and so on. So finally we have reached up to this part. Okay. So here we are using the Parseval's theorem. See what was it? So if you don't want to write it here, you can write in this part, because this is 1 by 2 pi. Actually it is 0 to 2 pi. Actually it is 0 to 2 pi. But since this integration is, sorry, the function fx is 1 for 0 to pi, so we are writing it 1 square dx. Okay, and this 2 pi we are writing on the other side, right? So this is what we are doing. This 2 pi we are multiplying here, and this becomes only pi, and then the entire series will be. So this is how we can work. Okay, this is how several questions may come. Another question, let us do. This is about the complex Fourier series. So suppose you have given a function fx which is equal to 0 and 1, 0 from minus pi to x to 0, and this is 1 for from 0 to pi. Okay, so you need to find out the complex form, com- complex Fourier series. You have to represent it in terms of complex Fourier series. So for that it's easy. You first check what is C naught, which is 1 by 2 pi, simple fx dx. So 0 to 2 pi fx dx, nothing else. So it will be 1 by 2 pi, 0 to pi will be 1 dx. So it will be pi by 2 pi, which will be equal to 1 by 2. So C naught is 1 by 2, we have got. What about Ck, which is 1 by 2 pi, 0 to 2 pi again? fx e to the power minus ikx dx. Correct? So 1 by 2 pi minus pi to pi is not the right way of writing. Let me show you. See, it is already been given that function is from minus pi to pi. So let's do it from minus pi to pi. Correct? So here also, let's do it from, let's do the integration from minus pi to pi. But minus pi to pi is 0, so we get 0 to pi e to the power minus I k dx. As from minus pi to 0, fx is 0. Okay, so we get 1 by 2 pi. What is this integral? Minus ikx divided by minus ik. This is how it is integrated. And finally, we get this. So 1 by 2 pi and minus ik you can take outside. And what about this? Okay, minus ik pi, right? So I know that minus iota kx can be written as cos of kx minus iota sin k. Now, if you have e to the power minus iota k times pi, then what it will be? Cos of k pi minus iota sin of k pi. This will be 0. So cos k pi will remain. So it will be minus 1 to the power k, because cos of pi is minus 1. Like this, we can write. All right. And minus 1, because sine of 0 will be 0. Let us also write this. Will be cos 0 minus I sin 0. This is 0. So this will be 1. So this is how we can write. Minus you can take outside, and yeah, so fine. Let us keep it like this. Now again, this is what ck. So ck will be equal to 1 upon pi I k when k is odd. Just check. If k is odd, it will be minus 2. 2 will cancel. Minus minus will cancel. And it will be 0 when k is even. Great. So this is done. Almost we are at the final step. So if x will be equal to c naught half plus 1 upon iota pi. Now this will be e to the power iota x by 1 plus e to the power iota 2x. I'm sorry, this is even. So odd will be there only, right? So by 3 plus e to the power 3, oh sorry, 5x by 5 and so on. This is how we can write. Okay. Also, just remember this is the complex form. So k minus will also exist. So be careful. So this will be minus iota pi, because k negative will also be there. Because you first write it, that's the best thing. C naught plus k is equal to minus infinity to infinity, k not equal to 0. Ck e to the power ikx. So k negative part, this is the k positive part. Okay, k which is positive. Now this part will be k negative. Just remember this whenever you are doing the complex Fourier transform. You must remember that this will also be the part which is going to come, the negative part. Okay, and so on. So this will be the key negative. All right. So this is your complex Fourier series. Okay. Now, in the next few 10-15 minutes, we try to complete the Fourier transform and do a simple question. Okay. Let's go for Fourier transformation. Not much a big topic, but how from Fourier series we are going towards the Fourier transform is an interesting thing. So now Fourier transform. Utility, is that if you have to change, say, from normal space time to wave number frequency domain, then this Fourier transform is extremely vital. You can see it in the quantum mechanics, you can see it in the geophysics, anywhere you find that this is extremely important, particularly for the processes like convolution. Okay, extremely important. The multiplication of the convolution becomes multiplication in the frequency domain. Okay, so all these processes, the physical processes or the mathematical techniques becomes easier in the Fourier domain, which is the wave number of frequency domain. So that's why it is always easy to transform from the space-time domain to the wave number frequency domain. So this is the application, okay, for the Fourier transform. Why we do Fourier transform? Okay, so we will try to see from the complex Fourier series. So let me write. So from complex Fourier series, we have fx k is equal to minus infinity to infinity. I am including everything now. Iota. Uh, let's, I think, write the entirety, that will be better. Okay, 2 pi k x by l. Now I will explain what I'm doing here. So we are writing b minus a is equal to l. A is minus l by 2, b is l by 2. So if you do b minus a, it will be l. Okay, so it's a l periodic function. This is for simplicity. For derivation, we are assuming, okay, l periodic function. So my c of k will be what? L 1 by l minus l by 2 to l by 2 fx e to the power minus iota 2 pi kx by l dx. All right. Write this expression fx summation k is from minus infinity to infinity. Ck, we are writing this into minus l by 2 to l by 2 fx e to the power minus I 2 pi kx by l dx. And in the summation, what is there? This. So you have to write that also, right? E to the power iota 2 pi kx by l. That's all. Fine. Now, suppose you have a length, a piece of length, whose length is actually L, suppose. And let us say I represent a wave with wave length lambda. Okay, this is wavelength. Okay, so that we can write if now k is the number of waves, therefore k into lambda will be equal to L. The total segment is divided into several k number of waves. So k lambda should be equal to L. This is the number of waves, one wavelength. So number of waves times the one wavelength becomes the total length of the segment. Okay, this is what the important thing. Now k by L will be 1 by lambda. Let's multiply 2 pi. K by L will be 2 pi by lambda. I define this 2 pi by lambda as something which is called the omega, called the angular wave number. Angular wave number. Okay. Now I know if I differentiate, say 2 pi delta k by L, what will happen? This will be equal to delta omega. Now we all know that what we write k, 1, 2, 3, 4, or -1, -2, -3, -4. The difference in K, delta K, is always 1. Always 1. So 2 pi by L is roughly equal to delta omega. Great. So we are using this. Okay. Now once we have done this, let's go to the integral again. So what we have written, fx K going from minus infinity to infinity. Here you have 1 by L minus L by 2 to L by 2 fx e to the power minus I omega x dx. Why am I writing omega here? Because you have 2 pi k by L. 2 pi k by L is omega. That's why I'm writing omega x. And outside it will be e to the power I omega x. Alright, this is absolutely fine. There is no problem. In the next step, we'll do some modification. K going from minus infinity to infinity. 1 by L as it is. I multiply by 2 pi. I divide it by 2 pi. So this is minus L by 2. 2L by 2 fx e to the power minus I omega x dx into e to the power iota omega x. Perfect. There's no problem in this. Okay. Now, another step. Same. C going from minus a to infinity. Now I write 1 by 2 pi minus L by 2 to L by 2 fx e to the power minus iota omega x dx and 2 pi by L e to the power iota omega x. Now, let's do an assumption. Let L tends to infinity. Let the segment, which is finite in our case, in the supposition, let that be infinite. In that case, what will happen is that delta omega will be equal to d omega, some differential. So fx will be, okay, now this L is infinity. Now come here. If L is infinity, this k limit will also go as an integral. So minus infinity to infinity, we can write summation to integration. This becomes 1 by 2 pi as it is. L becomes infinity, so it will be like this. Fx e to the power minus iota omega x dx. This integral is done. Outside, 2 pi by L is d omega, and this is e I omega. So what you are made of now, f of x is minus infinity to infinity, 1 by 2 pi minus infinity to infinity, fx e to the power minus iota omega x dx e to the power iota omega x d omega. I can still write this as fx as minus infinity to infinity. I am writing this as f of omega dx. Oh, sorry. Okay. F of omega e to the power iota omega x d omega. This is what you call as the inverse Fourier transform. Inverse Fourier transform. Then what is the Fourier transform? So the Fourier transform, which actually converts my spatial domain to angular frequency domain or time domain to angular, the spatial domain to angular wave number domain and time domain to angular frequency domain. This Fourier transform is given by f of omega. So what is this f of omega? F of omega is minus infinity to infinity 1 by 2 pi fx e to the power minus iota omega x dx. So this, you can see, a function in x is converted to function in omega. So this is what the powerful Fourier transform. Okay, so space or time is being converted to your wave number or frequency domain. This is what the Fourier transform is. Now, this 1 by 2 pi you can multiply in the inverse Fourier transform, and or you can do in both ways. So, what happens is that we generally write the Fourier transform as, without writing the 1 by 2 pi term, as say minus infinity to infinity f of x e to the power minus I omega x dx, and inverse Fourier transform as fx 1 by 2 pi minus infinity to infinity f of omega e to the power iota omega d omega. Okay, so this is the inverse. So now the frequency or wave number domain is being converted to x. This is how the Fourier transform looks like. Okay, now we can write some different things like Fourier sine transform and cosine transform. These are just simple forms. You can see that e to the power iota omega x is there. You can write cos and sine. So, Fourier transform f of omega is, generally we write root 2 by pi 0 to infinity, not minus infinity to infinity, fx, just simple sine omega x dx. And inverse Fourier sine transform is root 2 by pi 0 to infinity f omega sine k sine omega x dx. This is easy. You don't have any negative and something. And similarly, Fourier cosine transform. So this is the inverse. Okay, Fourier cosine is the same actually. There is no difference. So you have f of omega as root of 2 by pi 0 to infinity fx cos omega x dx, and the inverse one. So this is the inverse as simple root 2 by pi 0 to infinity fx, sorry, f omega cos omega x. Okay, so I think with this we can end, but yeah, okay. Here also there is a Parseval's identity. You can read further if you want. So Parseval's identity for Fourier transform is simple minus infinity to infinity f omega, that is in the Fourier domain, the modulus square, because it can be in iota also, right? In the Fourier domain, the modulus of f omega square d omega is equal to minus infinity to infinity the square of the original function fx square in the original domain to dx. Okay, so most of the Fourier transform and its use you will find in physics, in quantum mechanics, or in electronics. So when you calculate the capacitive reactance or inductance and all, we generally try to write it in terms of the Laplace transform domain or Fourier transform domain. Okay. So not much difference is there, but yeah. So this is important. Okay. So at last, let us just do one question and let's finish it. Okay. So let's do a question of Fourier sine transform set. Okay, fx is equal to e to the power minus a when x is greater than or equal to 0. Find Fourier sine transform. of fx. So it's a simple integration. So you can see, let us write I, the integration, the Fourier transform also. You can write f of omega also as 0 to infinity. Root 2 by pi, you can write, you cannot write, it's up to your choice, or let us write it for the time being. E to the power minus ax sine omega x dx. Okay, let's not write this as I. Let's write I is equal to 0 to infinity e to the power minus ax sine omega x. All right, and then solve them. Then last we will find the omega. Okay, so I, this we know that how we can write this. So it will be sine omega x integration by part ax by minus a from 0 to infinity minus sine omega x has to be differentiated once. So sine will become cos, and there is an integration of this also. It becomes minus a from 0 to infinity. Further, if you go, so it becomes sine omega x minus divided by a to the power minus a from 0 to infinity minus or plus omega by a, you can write 0 to infinity cos omega x e to the power minus ax dx. So I becomes sine omega x e to the power minus ax by a 0 to infinity plus omega by a. Now you integrate this, so you have cos omega x e to the power minus ax by minus a minus cos will be differentiated with the minus sign, so minus omega sine omega x e to the power minus ax dx with a minus a. So finally, what you are getting. So okay, if you now put here infinity, see this becomes 0, and if you put 0, this becomes 1, but sine of 0 is 0. So it is completely 0 plus. Okay, omega by a, you have cos of omega x e to the power minus ax divided by minus a from 0 to infinity, and minus minus becomes plus, this minus becomes plus, and this is a minus. So it will be omega square by a square sine omega x e to the power minus a. All right. What about this? This will give you, if you put infinity, this will be 0. And if you put 0, this will be 1. Okay. So finally, I will get omega by a square with a positive sign and minus omega square by a square. So it will be 1 plus omega square by a square I, which is equal to omega by a. All right. So finally, I will be equal to, so this is a square. Sir. So omega divided by omega square plus a. This is what you finally get, and therefore your f of omega will be root 2 by pi omega upon omega square plus a square. That's what. Okay, so this is your final answer you will get. All right. Okay. Fine. So this is, that's all for today. I think we can stop here. So what we have discussed, this is the Fourier transform we have discussed. So initially, we have started uh, with the simple harmonic motion. We saw that sine and cosine functions are mostly used in representing the waves because its properties are very well known. Okay, and but what will happen if you have some non-sinusoidal function? So we see that For non-sinusoidal function also, we can represent into sines and cosines if they are periodic and follow certain conditions, such as the Dirichlet conditions. If these conditions are satisfied, we can write any function in terms of uh, the general basis like cos and sine. Why cos and sine? You can see that they are forming the orthogonal sets, mutually orthogonal pairs. So that's why we can write. Okay, here you can write a naught or a naught by 2. Definitions will change, that's all. And this is a question which we have done. We have found out how to calculate a naught, ak, and bk, and then complex Fourier series, just writing the cos kx and sin kx, and including everything we are getting. This is the complex Fourier series. We solved one question about the Parsevals theorem as well as the complex Fourier series. Remember, in the complex Fourier series, the negative part also has to be included. Then we went for the Fourier transform, which is a transformation from the general space-time domain to the frequency wave number domain, where certain mathematical operations become easier and interpretations become easier. So that's why we generally do that. We have solved it from Fourier series, how to go to Fourier transform. We looked into that, and there are some sine and cosine transform. We use that to solve one question. Okay, so I think that's it for today. We can stop here. Okay. Thank you.